Hello class. So today we are doing the ANOVA lab session. So I'm going to show you exactly what you need to complete this week's lab session on Pearson. And after that, you'll get a little demo. So first things first, what are the key slides that you're going to need for today? So those are just slides from the lecture that you hopefully watched from days ago. Some of these slides are key and you're going to use them for all of the ANOVA questions that might come up. So here they are. These are the most important ones. So the first absolutely key slide is this one. You have to understand that the way ANOVA works is by splitting the variation. And how does it split it? It splits it between the sum of squares total, sum of squares among, and the sum of squares within. The second slide you're going to use for all of your one-way ANOVA questions is this one. So what does this table give us? It gives us for each, the among groups, the within groups, and the totals, it gives us degrees of freedom, gives us sums of squares, it gives us mean squares, and it gives us the F stat. And it tells us what the relationships are between all of these. So for instance, the MSA is just the SSA divided by the associated degree of freedom. And the same with the MSW, the mean square within is just the SSW divided by n minus c, the degrees of freedom. What else does this table tell us? What else does this slide tell us? It tells us, it reminds us that c is the number of group and n is the sum of the sample sizes from all the group, which is just a complicated way of saying this is the total sample size that you have. It also reminds us that the totals add up, which means what? N minus 1, that is the sum of this and that. So the degrees of freedom for the among, degrees of freedom within, summed up equal to the total degrees of freedom. And same for the sums of squares. SSA plus SSW equals SST. That was literally on the slide right before. Okay, so this relationship is the relationship in this column. This plus this equals that. Okay, last thing that you need to know, what is this F stat? The F stat is the MSA divided by the MSW, so it's the number here divided by the number there. And what are the associated degrees of freedom? The numerator has these degrees of freedom, and the denominator has those degrees here. So why is this table so important? Because you will get questions like this one on Pearson. It will give you a ANOVA table, it will give you some blanks, and you will have to fill in the blanks. You will, let's say, fill in this number from the text, and then you will fill in this number because you know that this divided by that equals this. So you can back out whatever goes into this box, right? You will have these kinds of questions. And so you need to refer to this table when you're trying to answer these questions. Now, just like in the previous chapters, when you need to compute a critical value, you can either do it from the tables, like the normal z tables, or the t distribution tables. Now we have the f distribution tables. Or you can get the critical value straight from Excel by computing it with a function such as f.inv.rt. So the same way we used to have a norm.inv and a t.inv, now we have an f.inv, and we can have an f.inv.rt where rt stands for the right tail. And remember, the f is asymmetric, and so you will always use the rt, meaning you're looking at the upper end of the distribution on the right tail. Now, what are the parameters of this f.inv.rt? The alpha, the degrees among, and the degrees within. Remember, the degrees of freedom among us are those of the numerator, degrees of freedom within are those of the denominator. So for instance, if you had this ANOVA output from Excel, you have your degrees of freedom here, how would you compute the critical value? You could get it from the table with the numerator degrees of freedom being 3, the denominator degrees of freedom being 44, or you can just plug it into this function f.inv.rt 0.05344, and it would give you your critical value. But luckily, you don't always have to do that. Sometimes Pearson gives you the full table, and the full table has the F critical right here. Or sometimes you've generated that table in Excel, and it gives you the F critical. But you can also just compute it just like we did, and you see that it is the same value. And of course, you can still use the distribution table that Pearson gives you. So here's another slide you need to be very familiar with. It's the one for the two-way ANOVA. How does the two-way ANOVA split the variation? Well, it's just a little bit more complicated. Instead of having SSA and SSW, it has SSA, SSB, SSAB, and SSE, okay? 4 components. So variation from factor A, variation from factor B, variation from the interaction, and then the random variation that's left over. What's important on this slide, particularly, are the degrees of freedom. Each of these sources of variation has a certain degree of freedom, and you don't need to remember those by heart. Why? Because you have this slide. So keep this slide handy. Remember, the sum of these is equal to this. And of course, this leads us to the next table, the same table we had before for the one-way ANOVA. Now we have it for the two-way ANOVA. And what does it tell us? It gives us the sums of squares, the degrees of freedom, the mean squares, and the f's coming from all of these sources of variation: factor A, factor B, AB interaction, and error. Again, you will get questions where you have this table but with blanks, and you will need to fill in the blanks. And so how do you fill in the blanks? By knowing what the relationships are between these cells. Okay, here's another concept that I've insisted on in the lecture and that you need to be familiar with, is that when there are interaction effects, the interaction effects give plots where you have non-parallel segments, where some of the segments cross with each other. Okay, so when you're doing a two-way ANOVA analysis and you plot the responses by factor, if they don't cross, it means you do not have interactions. There are no interaction effects. If they do cross, it means that you do have interaction effects. And Pearson will ask you to do this, so you should be ready to give these answers. You will, for instance, get questions such as this one, where they ask you which of these graphs is the correct graph for your question. Now, there are two ways to do this. One way is to actually go and compute the numbers, right? You have data they gave you. How does this data relate to these pictures? Well, one of these dots is the average of these 4 numbers, another one is the average of those 4 numbers, another one is the average of those, and another one is the average of those. So you could very well compute your 4 averages and figure out, okay, for strength equals 1, I have this and this, and for strength equals 2, I have this and that. And you can try to figure out how these 4 values will be matching only one of these 4 plots. So one thing you can do is just compute the average by cell and see which graph fits best. Now you got to be careful because one of these factors is here on the x-axis, so that is the strength 1 and 2. Now this axis, the y-axis, is not the second factor. That in this case is your outcome. It's the outcome that you're trying to measure by factors, right? So remember, in a two-way ANOVA, you have 3 variables. You have the outcome and 2 factors. So the outcome is the density. The first factor is strength. And the second factor, how do you see that? Well, that's the color, or it's the type of line. The full line is one value of the factor. The dotted line is the other value of the factor. But so how do you read this? Well, here you can clearly see that when strength increases, the lines drop. So this is clearly a negative impact of strength. Here you have the opposite. As strength increases, goes from 1 to 2, you get a positive impact of strength. The third one is trickier, but it tells us something about factor B. In this case, factor B is time. What does it tell us? Well, it tells us that from one value of factor B, which is the full line, to the other value of factor B, which is the dotted line, the values of density go up, right? Both of these points are above both of these points. So this tells us what? This tells us that factor B has a positive impact. It raises the density. So 2 things about this. First of all, be careful. Factor A is on the x-axis, but factor B is not the y-axis. Factor B is full line versus dotted line. Second thing is that if you already did the analysis, if you already did your ANOVA table, you already know whether there's an impact of factor A or an impact of factor B or an interaction impact like this. And so you don't actually need to do all of this, because if you've answered the previous questions correctly, you should be able to just eyeball what the impact should be, and the one that matches your ANOVA analysis is the correct answer. Okay, here are a few more slides about how to actually run ANOVA in Excel. So the first thing you need to do is enable the analysis tool pack. Most of you have already enabled the analysis tool pack. If you have not, the exact procedure will depend on whether you're using a Mac or a PC, and it might depend on your version of Excel, but I can show you the slides of how it works on my laptop. So on my laptop, what I had to do was go into Tools and then Excel add-ins. And then in the Excel add-ins, this table would pop up and I just ticked the box that says Analysis Toolpack. Then you click OK and you should be good to go. And then what happens, this option appears right here in my Excel screen. Now that's in the Data ribbon, totally on the right. That's for me. It might be a little bit different for So how do you run a one-way ANOVA? Well, you click on that data analysis button, and then there's a pop-up menu in which you're going to select ANOVA single factor. That's one-way ANOVA single factor, okay? Single factor means one way for Excel. So this is data for a one-way ANOVA. You see there's data divided by 4 values of a given factor, which is the company. What do you need to tell Excel? You need to tell it what the input range is. So in that case, it's everything. You select the names together with the data, and then you click Labels in first row. These are the labels. Then you need to give Excel the alpha. The alpha will be given to you by the question. And then finally, you can tell it an output range, or you can have it appear in a new worksheet. My preference is always to give an input range within the same worksheet, but it doesn't have to be your preference. Moving on to two-way ANOVA, how would you do one of those? This is the type of data you will have. How do you know that it's a two-way ANOVA? Well, because in addition to having different columns here for one of the factors, you have two subtypes here in this column. So this is one factor and this is your second factor. Now, importantly, Excel gives you two options. It gives you an ANOVA for two factors with replication and an ANOVA with two factors without replication. What does replication mean? It just means that you have several observations, several values for each combination of a factor A and a factor B. In this case, it's obvious that you have replication because you have 5 values for each combination of a factor A and a factor B. So this is with replication, just meaning that each cell has several observations. And here you have 5 observations per cell. And again, what do you need to give Excel? You give it the input range, which is your entire range with all the names. Then you have to give it an alpha, which again comes from the text. And then you have to give it an output range, which you can put wherever you want. I put it in A13 right here. Importantly, you have to add this number, which Excel calls rows per sample. What does rows per sample mean? Rows per sample just means the number of values in your cells. This, remember, is what we called n prime in the lecture. So here you have 5 values in each cell, and so you put 5 in your rows per sample. What comes out? This big table comes out. The important part of this big table is actually down here. This is the table that contains all the values that you will use to answer almost all the questions that might be thrown at you from Pearson. So the table, for instance, gives you the p-values for each of the sources of variations. Now, importantly, Excel doesn't know what the factors are. It doesn't know what factor is called inhale or front or kiosk or expert, and it doesn't know what factor is no here and yes here. It's not going to tell you mobile payments either. It gives you generic names, one that it calls sample, one that it calls columns, one that it calls interaction, one that it calls within. Okay, sample is this factor, the factor that's in the rows. Columns is the factor that's in the columns. That's pretty self-explanatory. Interaction is the interaction between these two, and within is what is usually called error as well. So it's the residual error. But note that this corresponds exactly to the table that you've seen in the lecture notes. So here is a slide that recaps this for you. First row, sample, is the effect of row groups. The second row is the effect of column groups. And the third row is the effect of interaction. This slide reminds you how to compute these degrees of freedom. Sample degrees of freedom are r minus 1. So it's the number of groups in the rows minus 1. We had 10 rows, but we only had 2 groups in the rows, right? So this is 2 minus 1. The columns, there were 4, so the degrees of freedom are 3. The interaction is 1 by the other, so it's 3 times 1. It's also 3. And what about the within degrees of freedom? Well, that one is the only one that's a little difficult. It's r times c times n prime minus 1. So what was r? It was 2, 2 factors in the rows. C was 4, 4 columns in the other factor. N prime was what? The number of observations per cell. So that was 5 minus 1 equals 4. So 2 times 4 is equal 32. Another very important point for your lab, you will always look at the interaction first, okay? Always look at this row before you look at these two. If this one is insignificant, then you can start looking at those. If it is significant, then those do not have meaning. So you have to start with this one. You start with the third one counterintuitively. You might ask, when do I use which ANOVA? When do you use one factor versus two factor ANOVA? Well, if you see a table like this one, where you have one factor divided into different values, 3, 4, 5, 8, this is a one factor ANOVA because all of these are different values of one factor. On the other hand, if you see a table like this, which has one factor divided into values here and a second factor divided into values there, that is a two-way ANOVA. So one factor one way, two factors two way. And again, almost always you will have to do something called the two-way with replication because you will virtually always have multiple observations within each cell. Here's an example where that is not the case. You have blend X, blend Y, blend Z, 4 types of grains, but in this case, you do not have multiple values per cell, and so it's a two-way without replication. But this will not happen often. And hopefully you can enjoy this little meme that makes fun of ANOVA a little bit. So you can make fun of ANOVA if you want because it is kind of like putting variations in your variations so you square sums when you square sums. But ANOVA is really important. Everybody uses it in real life. It's really a ubiquitous tool and you are better off knowing about it and knowing how to use it.